Hey everybody, Professor Davis here from ChemSurvival.com and the YouTube channel ChemSurvival, and today I'm going to give you a brief introduction to UV visible spectroscopy and the Beer-Lambert law. To begin our discussion, I've drawn a schematic on the bottom half of this screen depicting a fairly typical setup for a UV visible spectrophotometer. Now there are many different ways to build a spectrophotometer, but this is one of the simpler designs, so I thought we'd start there. It consists of a source lamp, which is something as simple as the headlamp from a motor scooter, or more complicated like a deuterium lamp or xenon arc lamp. The next device in line is what's known as a monochromator, which is two slits which separate, or are separated by, a prism or a diffraction grating. The next element of our spectrophotometer is what's known as a beam splitter, which divides a beam of light into two equal parallel beams of light. Next is the sample compartment, which contains cells for both a reference and a sample. And finally, detectors, which are devices that convert the impact of photons into electrical current that can be monitored by a computer. So now that we've defined each of the smaller pieces within our spectrophotometer, let's turn it on and see what happens. I'll ignite the source lamp, creating a variety of wavelengths of different light. This light passes through the first slit of the monochromator, ensuring that all of those light photons are traveling along parallel pathways, so that when they strike the prism, they are refracted into a rainbow of colors. So each wavelength of light is moving to a different place in space. So only one wavelength of light in this situation is going to make it through the second slit in my monochromator, striking the beam splitter and becoming two beams of equal intensity. These two beams of equal intensity will traverse a cell, a different one for each of course, one being the reference and one being the sample cell. As the beam exits these cells, it strikes the detectors, which are firing away, creating an electrical current. And you'll notice at the moment that the intensity of the light exiting both the reference and sample cells is identical. Therefore, the current generated by each detector is identical. So in this case, the intensity detected by each of my two detectors are the same. So if I were to consider the ratio of the intensity leaving the sample cell to that leaving the reference cell, I see that the transmittance of my sample cell is 100% that of the reference. So I'm going to plot that here at 0 concentration, 100% transmittance. Now let's add a little sample to that cell, something that might absorb this light. Now notice that when I do this, the intensity of the light exiting the sample cell has decreased, and therefore the current generated by its detector has also decreased. So now the ratio of intensities is no longer 100%. In this case, let's say that it's down to 50% at a given concentration, which I'm going to call X. If I add another equivalent of my sample to the sample cell, that decreases the intensity even more. Not only that, it decreases the intensity at the sample cell by a known amount, exactly 1/2 for each equivalent of sample that I add. So when I compare my new intensities at the sample and reference cells, I see that I'm now at 25% transmittance. And similarly, an incremental increase in the concentration once more in my sample cell leads to another reduction by 50%, and therefore a percent transmittance of 12.5. Now we have enough data points to see something very interesting here. The relationship between the percent transmittance and the concentration of a sample is not linear. Instead, it's exponential. And while it's very useful to have this information, scientists and spectroscopists prefer, if they can, to discuss linear relationships within their data, because this makes for a much simpler discussion and it's much easier to predict how things will behave if we have a simple linear plot to compare. This is where the Beer-Lambert law comes in. You'll notice that right now I have an exponential relationship between my percent transmittance and my concentration. We can see that in the equation here, where the concentration is a term up here in the exponent. But August Beer did was to convert that percent transmittance into a new unit called absorbance. And he did so by taking the logarithm, or really the negative logarithm, of the transmittance. Taking the logarithm of an exponential function creates a linear function. And so the data, when plotted as absorbance rather than transmittance, is actually considerably easier to look at. Not to mention, it's much easier to predict the exact absorbance by either extrapolating or interpolating within the data set that I've collected. This is the utility of the Beer-Lambert law, and the reason why we convert percent transmittance into absorbance so often when conducting UV visible spectroscopy. That's all for now, everyone. I'm Professor Davis from ChemSurvival.com and the YouTube channel ChemSurvival. I'll see you on my next video. I'd like to thank everyone for making ChemSurvival.com and my YouTube channel ChemSurvival such a success. And I'd also like to invite you to check out a new project I've been working on coming in October 2014. It's a 36-part organic chemistry course developed in collaboration with the Great Courses. To get more information about my course, go to www.chemsurvival.com. That's www.chemsurvival.com. Thanks again for watching, everyone, and as always, I'll see you on my next video.